Good morning, everyone. Thanks for attending this session. Today I'll be talking about error-aware time synchronization protocol, which is specifically designed for reconfigurable data center networks. This work was majorly led by Yiming, Jialong, Zhengqing, and Yiting at the Max Planck Institute for Informatics. So as Moore's law slows down for merchant silicon, we need to find new ways to scale data center network bandwidth. And reconfigurable data center networks is one answer to this problem. The basic idea is to replace the electrical packet switching core with optical circuit switches. Optical circuit switches are very energy efficient and cost effective, and then they provide a high bandwidth alternative to power hungry electrical switching ASICs. But the trade-off with optical circuit switches is that they provide one connection between a port pair at a given time. Therefore, if you want to emulate an all-to-all connections like a packet switch network, we require a controller which basically cycles through a schedule, and in the schedule, during each time slot, it will connect different pairs of nodes. And some of the modern optical circuit switching switches can reconfigure circuits on microsecond or even nanosecond time scale. Now, because of circuit switching, time sync becomes essential in any reconfigurable data center network. Note that in traditional electrical packet switch data center network, time sync is typically an application requirement. Whereas I'll show you that in reconfigurable data center network, time sync actually is a routing requirement. Let's see how. So because circuits appear and vanish in reconfigurable data center networks, we need to make sure that the data must land within the circuit window. So if we miss the window, the packet can get dropped, or it could be delivered to an unintended node. So basically, in reconfigurable data center networks, clock sync is needed for nodes to know when to send packets for a desired destination. So what exactly is the reconfigurable network's requirements for time sync? The key requirement is that the packets must not be sent during OCS switching. OCS switching is basically a time window between circuit reconfigurations during which no circuit is active. And for this reason, reconfigurable data center networks have a concept of a guard band. Guard band is essentially this interval where no packets are sent, and it essentially prevents packets from being sent at the wrong time. Now, if the guard band is set aggressively small, then there may be a case that due to time sync error, packets are sent during OCS switching and then they get dropped. On the other hand, if the guard band is set conservatively large, then it leads to bandwidth loss. For example, if we set the guard band about 10% larger than the OCS switching, then it leads to 10% loss in bandwidth. So the right size for the guard band becomes that it should be 2 times the worst case time sync error plus the OCS switching time, because this is going to ensure that there is no packet loss during OCS switching because of a misjudged time sync error, and the bandwidth loss also remains minimum possible, but it is still proportional to the maximum sync error. Now, consider an example reconfigurable data center network design where we have a time slice duration of 2 microseconds. If we want to achieve 99% network utilization for this reconfigurable data center network, then if you do the math, the maximum sync error comes to be around single-digit nanosecond range. So overall, the time sync requirement for reconfigurable data center networks is the following. First, the worst case sync error must be bounded, and this error bound must be within single-digit nanosecond range for modern microsecond scale circuit switching. So why can't existing time sync solutions meet these requirements? The main reason is that existing time sync solutions are designed for static data center networks, and therefore they rely on a static spanning tree which is rooted at a reference clock. But in reconfigurable data center networks, the topology changes rapidly, and therefore it disrupts the clock propagation trees. A recent work called Firefly is somewhat robust to spanning tree disruption. This is because it uses gossip averages of peer clocks, and it does not rely on clock propagation trees. However, averaging does not give us a tight worst case bound on the sync error, which is exactly what we need in order to size the guard bands in reconfigurable data center networks. So the key research question we answer in this paper is how to design a time-sync protocol for reconfigurable data center networks with a nanosecond scale sync error bound. And our answer to this question is that nodes must sync wisely. The key insight we have is that each node can predict its current sync error bound based on pre-profiled drift and hop error bounds. And then based on this key insight, the key idea is that each node only synchronizes with neighbors whose predicted error bound is lower than its own. I'll first explain you more about the key insight. So why does sync error bound can be predicted? Let's start with the sync error analysis. So there are two sources of error every time a node synchronizes its clock with another node. The first is the hop error. It is essentially the noise in each sync operation, and it basically comes from inaccurate timestamping and delay asymmetry. The second error is the drift error, which is caused by frequency difference between two clocks crystals. So after every sync operation, the clocks of the two nodes eventually drift away as time goes on. Now, since the clock is propagated from a reference node, we can formalize this error along the entire synchronization path with the following equation. The first term here represents the accumulated effect of the clock drift, whereas the second term shows the sum of the multiple hop errors. Now, this equation for error involves multiple runtime variables, and these variables are not known at runtime. Therefore, the error is also not known at runtime. However, the maximal value of this equation is actually predictable at runtime. And this essentially means the sum of the maximum variance and the sum of the maximum possible hop errors we have accumulated. Why is that predictable? This is because drift is not completely unpredictable. Prior measurement work has shown that drift is mainly influenced by temperature and it has a small runtime variance. Prior measurement work has also shown that hop error follows a distribution, but it still has a clear range. What this means is that nodes can actually track their own error bound in the following way. So before the reconfigurable data center network starts operating, we can actually pre-profile each node's maximum drift variance and a network-wide bound on the hop error. And then during runtime, each node can track the sync error bound. So as time passes, the sync error bound increases with the drift variance. Every subsequent sync operation, the error bound increases by one more maximal hop error. So based on this above insight, we design the error-aware synchronization protocol. The basic idea is that nodes keep track of their own error bounds, and they only sync with nodes which can reduce its error bound. Essentially, the nodes sync wisely. For example here, node J will synchronize its clock with node I only if the error bound on node I plus the hop error involved in this synchronization operation is less than node J's current error bound. Let's run through an example. So here we have a reconfigurable data center network with 6 nodes and changing topology. Node 0 has the reference clock. Now, in the beginning, we initialize each node's error bound to infinity except for the reference node 0. In the first time slice, every node looks for neighbor nodes that can reduce its error bound. So in this case, for node 1, node 0 can reduce its error bound. So node 1 will synchronize with node 0 and it will inherit node 0's error bound of 0 with the addition of the hop error bound because of one sync operation. Now as time passes, the clocks on all the nodes will drift and therefore every node will increase its error bound by its maximum drift variance. So in this case, node 1 has a maximum drift variance of 7 nanoseconds per slice, so it increases its own error bound by 7. Node 0 is the reference node and so its drift variance is 0. Now again, in time slice 2, every node looks for its neighbors and see which neighbor can actually help it reduce its error bound. So in this case, we can focus on node 4. For node 4, if it synchronizes with node 1, it inherits node 1's error bound of 12 with the addition of the hop error bound. And again, as time passes, every node updates its sync error bounds based on the drift variance. Note that the drift variance can be different for different nodes because it's the physical property of a node's clock oscillator. Now again, node 4 this time has an even better neighbor, which is node 2 with a lower bound, and therefore node 4 will synchronize its clock with node 2 and will inherit node 2's error bound of 10 with the addition of the hop error bound of 5 and so on. So this error-aware time synchronization protocol has two key properties. The first is that for given circuit schedule, it achieves the minimum possible sync error bound over all parent selection choices. And the second is that when we have a periodic reconfigurable data center network topology, this error bound itself is periodic and it is fully pre-computable offline. What this means is that we can have this error bound pre-computed offline, and therefore the guard band that we want to set can also be computed a priori. We have a detailed proof for these two properties in the paper. But the key implication of these two properties is that reconfigurable data center network designers can now determine the tight synchronization floor for their fabric before choosing the guard bands. Now, in order to implement this error-aware synchronization protocol, we could implement it as a distributed protocol at any layer. In our prototype, we implement it as an Ethernet protocol using Tofino2 programmable switches. So the figure here shows the SyncWise header. It has a clock timestamp together with the corresponding error bound. We also develop an event-driven simulator for extensive simulation and comparison, which we have open sourced. Now let's look at some of the key results from the simulations. So in simulation, we have 108 Tor switches with 6 optical uplinks and a round-robin circuit. For baselines, it is hard to find truly comparable baselines to SyncWise since it is first of its kind. So we use sync protocols from static data center networks and adapt them to reconfigurable data center network where possible. So the figure here shows the CDF of the clock synchronization error for various schemes that we have compared in our simulation. So we can see that for SyncWise, the error remains under 9 nanoseconds maximum error bound, which is 2.5 times better than Firefly and 3.8 times better than Graham. We also stress test SyncWise under diverse setups. Essentially, we vary 3 key parameters that influence the sync error: the sync interval, the max drift variance, and the hop error bound. Again, we see that under all conditions, SyncWise maximum sync error remains minimal compared to the other baselines. So, to summarize, bounded time sync is an essential building block for reconfigurable data center networks. In this paper, we show that nodes can predict their sync error bounds and thereby perform error-aware synchronization to achieve provably tight bounds. And finally, error-aware synchronization is a general principle which is applicable beyond reconfigurable data center networks. Thank you, and I'm happy to take questions.
Okay.